implementation of an S-version finite method for analyzing elastic plastic problem. The co-authors are Naoto, Mitsume, Naoki, Morita from the University of Tsukuba, and Kazuki Shibanuma from the University of Tokyo. This is the outline of my presentation. First, I will shortly introduce the background of the research, and then introduce the superposition finite element method. And I will introduce the implementation of the superposition finite element method for analyzing elastic plastic problems. Before I summarize this presentation, I will show you some simple applications. Finite element method is a powerful tool for structure design and failure analysis. However, when it comes to the stress constraint problem or the crack problems, to get the accurate numeric predictions, we need to reduce the element size or increase the shape function orders to get the accurate numeric predictions. However, that will increase the numeric cost. For example, for the brittle crack propagation problems, usually the brittle crack propagation problems is designed based on the dynamic stress intensity factor. That parameter has been approved to depend on the test temperature, the crack propagation velocity, and also the crack length. Recently, in the University of Tokyo, the researchers proposed that the height of the crack tip at a certain distance. Here we use RC. At this distance, the fracture stress is almost constant. Here we have some experimental evidence here, and we test the two steers, and the value is almost constant. However, the critical length here is in the range of 0.15 to 0.25 millimeters. For the application of this criterion to actual structure, for example, to a sheet, there will exist a skill gap. How to solve this problem? The superposition method, the superposition finite element method presents to be a possible solution. The superposition finite element method discretizes the problem domain by two sets of mice. First is the global mice. The problem domain is discretized by the global elements with relatively coarse element size. And in the domain of interest, for example, along the crack tip, another side of we call the local mice is introduced and superposed like a paste to the global mice. And this is the superposition. And we got the equilibrium equation of this superposition finite element method based on virtual power law. And this is the same metric. We have this KGT and KL, which is the same in the standard FEM. And we have the carbon stiffness matrix KTL and KLT, which establishes the relationship between the global mice and the local mice. And after solving this equilibrium equation, we got the displacement from the global mice and from the local mice. And here we perform the superposition. In the domain of the superposition zone, the displacement from the local mesh and the global mesh are superposed. And outside of the superposition domain, we only use the displacement from the global mesh. Here is an example of the displacement field of a crack problem. Here, this is the domain, and we apply the global mesh, and around the crack tip, we apply this local mesh. And this is the solution of the global displacement field, and this is the solution of the local displacement field. By superposition this displacement from the global mesh and the local mesh, we get this field. We get this solution of the displacement field. And this is an example of the displacement. For the implementation of the superposition finite element method, the main problem is the calculation of the company stiffness matrix, KTL. Since due to the superposition, we may expect that for some local element, it belongs to two global elements because we need to calculate the global shape functions. So in the conventional finite element method, the integration assumes the continuity of the element. However, for the superposition finite element method, the local elements they present the discontinuity due to the superposition. How to solve this problem or how to improve the accuracy of the stiffness matrix? Here we apply the two methods. The first method we call the age refinement method. Here I presented here the 2D example. Indeed, we apply this. We implemented this method in 3D, and we introduce a parameter we call HRE. Use this sorry. If this parameter equal to 1, this is the original element. If this parameter equal to 2, we divided this element averagely in each direction. And if this parameter equal to 3 and 4, when the parameter we prove that when the parameter is larger than 8, we can accurately obtain the stiffness matrix. And another method we subdivide the element is that we only enrich the element, enrich the sub-elements, leaving the discontinuity. In this case, we can reduce both the subdivided elements and the integration point. And then we can calculate the carbon stiffness matrix KTL and KLL based on the subdivided element integration point. And for the KTT, for elastic problem, since this D matrix is constant in the element, and the shape function only from the global elements, so we have no problem for the calculation of KTT. However, when it comes to elastic plastic problem, we need to update the constitutive matrix, this D matrix, which depends on the equivalent plastic strain hardening, and also the plastic flow. Due to the superposition, some global elements may also present this discontinuity. For example, as I marked in right here. So in this case, the global element also lead the element subdivision. And after the application of element subdivision to both the global element and the local element, we can calculate the internal force in elastic plastic analysis. And note that in the elastic plastic analysis, we superimpose the strain and we do the update of stress. Use the micro method or cutting plane method. And for the calculation of internal force, we need to calculate the stress from the global mesh, sigma G, and sigma L from the local mesh. Usually, the local element has smaller element size than the global element. So we propose a strategy to calculate the stiffness matrix KGG based on the integration point in the local mesh. For example, here we have a global element, and we have this local mesh. We integrate the stiffness matrix of this global element by two parts. First part is as marked in green. This we apply the integration point from the local mesh, which located in the global elements, and the other part is the integration point from the global element only. So this is the expression for the calculation of stiffness matrix. And with this strategy, the global element can be categorized into three groups. The first group is the global element fully located outside of the local mesh, and then we can only use this part in the standard finite element method to calculate the stiffness matrix. For the global element partially located in the superposition zone, we should use these two parts to calculate the stiffness matrix. And if the global element is fully located inside the local mesh, for example, as marked in pink here, and we only need this part for the calculation of stiffness matrix. In addition, with this strategy, we can directly use the superposed stress to calculate the internal force. We don't need to calculate the stress component from the global mesh or the local mesh. And finally, come to the application. First is the elastic application to verify the accuracy of this method. We have a plate with a hole, and this is an elastic program. Under we have the tension stress, and the stress is 1 megapascal. Analytical solution shows that the stress concentration factor here is 3, and we have this global mesh and local mesh. This is the superposed mesh, and we calculate the stress field, and the stress here is very close to 3. And we also perform the elastic plastic analysis, and we compiled this is the result from the conventional finite element method, which very fine element size. And we can see that the stretch field and the string field shows very similar. And we compiled the accuracy of this method with the conventional finite element method. Here I present 3 sets of finite element calculations, and both the number of elements and loads are presented here. And with the element size decrease, and also presented 2 sets of calculations from the SFEM. And we compile the stress along the whole. And we can see that the result from the SFEM case 2 shows very good agreement with the result from the conventional finite element method case 3. But the number of elements and nodes is only 10% of this conventional finite element method. This also applies to the stress in y direction. Another application is the Pareto problem. This is the domain we analyzed, and this part we only selected this small part for analysis. And we have this global mass, and label in the crack we have this local mass. And we also compare the results with conventional finite element method. And this is here I only presented the stress contour and the equivalent plastic contour to compare. We can see that in the superposition domain, the result shows good agreement with the conventional finite element method. However, we should notice that both the number of elements and loads are much less than that of the conventional finite element method. And here is an example of the dynamic vector propagation with the superposition finite element method. However, this is only an elastic analysis. Yeah, and for the analysis of the elastic problem, elastic plastic analysis with dynamic vector propagation, we are developing the code at present. And finally comes the conclusion. First, we have implemented the Western finite element method for analyzing elastic plastic problem, and the efficient strategy for deeply symmetric formulation has been proposed. And this superposition finite element method is accurate with less degrees of freedom. And the last one is that this method is promising to be applied to both static problem and dynamic problem. Thanks for your attention.
Thank you. Questions, please? Yes.
Thanks for that. It looks really great. If you are applying your displacements from a coarser mesh to your more refined superimposed mesh, how can you be sure that the displacements from the coarse mesh are as accurate as they should be for the fine mesh?
I will find the displacement field for the correct programs. Yeah, this one. This is the displacement field from the global mass. And for elastic problem, we have the analytic solutions, and we compile the solutions. And this solution of displacement from the global mass only is not accurate indeed. And that paper has been published in 2020, and we compare the displacement field. And after the superposition of the displacement from the local mass, we can get a high accuracy of displacement as presented in this figure. So we compiled with the analytic solutions in 2D and 3D both.
One more question, please.
So what's the advantage of your method with respect to the sub-modeling method as it is implemented in Abacus, for example?
Sorry?
What's the advantage of your method with respect to sub-modeling as it is implemented in Abacus?
Okay, the first advantage I think for this method is the flexibility in the domain discretization. For example, we for the global domain domain we discretize the domain with the host elements, and we only need to design the match pattern in the domain of interest, such as the stress concentration or the crack tip. That is the first advantage. The second advantage is the accuracy. We compared with the conventional pattern element method, and we found that reaching the same accuracy, the degrees of freedom is greatly reduced. That are the advantages, I think.
Okay, the last question.
Okay, quick question. It looks like in Alex we have a submodel. So we run the cost measure there then with interest to new zero.
Yeah.
So then we do a submodel there. Then this submodel is applied eroded by displacement, as you asked. Displacement. Then you can measure this area and then to the more detailed solution there. So very quickly, what's the difference between your superposition method and this submodel method? So what's the difference? It looks like you apply the not boundary condition is not displacement boundary condition. It's applied not force. So is that different?
I think for the method available in Abacus, that is only you use the conventional finite element method twice. But in this method, these two sets of matches are calculated simultaneously. In Abacus, you do the calculation first, and then you get some solution, and you run the summation again, right?
Yeah.
Yeah, but that is you always use the conventional finite element method. But in this one, we introduce another site, and these two sets of match are calculated at the same time, and we can obtain the solutions more accurate. That is the difference, I think.
Okay. You think your solution is more accurate right now?
For example, if we compare the accuracy, we should be honest that we use the same degree of freedom or same element size. We compare, then we can judge which one is accurate. If we compare, for example, if you use a very fine element with conventional finite element, and you compare the result with this method, maybe we have the same accuracy. So it is not equal to judge here.
Well, the discussion is quite interesting, but we need to move on. So thank you.